Hello, I am Austin Marler, a studying mechanical engineer working under Dr. Rajabali to research building a new ion source for the Tennessee Tech ion beam. This project began with a used cesium sputter ion source our team inherited from the Oak Ridge National Laboratories. This source used an electric heater to warm cesium so much that it ionized. While functional, the device required 400 amps and 16 kilowatts to operate. Thus, my job began in search for a more efficient ion source. After considering several types of ion source, the decision was made to pursue a laser ion source design due to the much lower electrical cost, higher ion count per watt, and an existing laser source on campus. Here in Figure 1, you can see the current design that the ion beam relies upon to function. This is primarily made from parts of the cesium source and only a few newly designed pieces to save on cost. A laser ion source uses an intense pulse of light to ionize the source material and create a plasma at the area of laser interaction. These ions are created so that we can easily manipulate their speed and position using differences in voltage potential and magnetic fields. A laser ion source can produce an inconsistent output of ions when the same target location is heated or ionized repeatedly, so the target is placed on a rotating and translating surface. These 2 degrees of freedom allow us to scan the entire surface of the target, allowing for more consistent results and less downtime between maintenance operations. The laser beam lies on the right side of Figure 2 in order to achieve the smallest angle of incidence for maximum efficiency without disturbing the ion beam and contaminating the optics rapidly. On the left side, you can see a simple design for the target manipulator consisting of 2 NEMA 17 motors, one to lift and one to rotate to trace the pattern you see in Figure 3. In order to design an ion source, which can be a difficult, timely, and costly process to calibrate and redesign, it is best to simulate proposed designs to learn and build from. Using IBSimu, a free ion optic and extraction simulation program, the source shown in Figure 1 can be tested without constructing a physical object. Since the source is radially symmetric, only half of a 2D slice needs to be simulated upon to produce what you see on the right side of Figure 4. The red bar represents a few thousand ions traveling from left to right. The blue represents charged surfaces, and the faint green lines represent the gradient of potential within the space. The goal is to narrow the red beam, without having it flare out uncontrollably by the time it enters the long blue bar on the right. For now, the source exists only in simulation, but the predicted results are promising, with an expected increase in useful ion generation and decrease in power consumption by about 14 kilowatts. In the future, another ion simulator called SimIon will be used to better refine the design. The source manipulator will be completed and fabricated, and the emittance plot will be investigated for more efficiency improvements. This work was supported by the Sizer Grant through Tennessee Tech and the Department of Energy. Thank you very much for your time.